Meme sawa.
I hope you have this recording and also you have this note. Okay. See, manufacturing B1. Yes, B2 is here. So this is your note. Okay, Buddha? So you have to understand this. Okay, we have tried our best to explain this. Go through this, and this is an essential knowledge. Okay, this is an essential knowledge. You have to go through this and understand, and notes are there. Your standard note I passed to you is about this. Okay, it's about this, and then this is the very first section of the revision 1. Okay, so this is very, very important for you to score, because this one, when it comes to thermodynamics, yeah, of course, it's a very good subject, but if you need to score, well, you have to answer well. Yeah, because in thermodynamics like subject, this is a very grand subject. There are no free marks. Yeah, there are no free marks. So you should remember that, because it's the nature of this subject. So you have to look into this subject very seriously. The other way, even though there are no free marks, there is a huge potential to get you A+ mark. Yes, because you can answer this easily once you understand. So there is no way denying marks for you if you answer well. Okay? Yeah. And also the other way, if you don't answer well, there is no way giving you marks. So the two sides, but we will take the positive side and try to look into this even exam point of view. So I'm ready to give you the full marks. You should be ready to answer very well. And this is a very special subject, and this brings you a very good future. Okay. So here understanding is very important. Even here about dryness fraction, some understanding what the dryness fraction means. Yeah, these things are very important. The meanings, the physical sense behind these words, okay, are very important for you to know. So if I'm not mistaken, this is a coursework I passed to you. So those who did not do this assignment, please do it and send it to me. This is one of the component, and the other is, yes, of course, item 1 is the table 3. Okay, item 1 is table 3. It's in your notes. So please look into this. Okay, so this is very essential. Basics you have to know. Okay, so it's totally on you to look into this. Okay, and I have done the necessary, the theoretical aspects of this. And we talk about irreversible processes as well. Okay, means this is because of the friction and also sizable temperature differences for compression and for expansion. See, the same words are here. Okay, the maximum expansion work out when it comes to isentropic expansion. So the same way in reverse, for compression we need the minimum work. So minimum possible work again with isentropic compression. We call it ideal work on compression. Divided by actual, this will give the isentropic efficiency of compression. Okay, this I extract from your notes. Okay, So notes with you for quite long time. Okay, so you have to understand this. Okay, so don't rely on memory, but rely on some understanding. Yes. In the exam, okay, some formulas, example, this work done. Okay, so this will be given. Okay, this will be given. So polytropic processes, I have done this in balloon example and also in some cases. So PV to the power n equals constant. Can you remember? Yes, you have to understand polytropic process. Okay, yeah. And also constant volume processes and constant pressure processes. This all for the non-flow closed system. See, net heat plus net work is the rising of internal energy. Per unit mass, this is small letters, Q, W, and U. 1 is the initial state, 2 is the final state. Okay, for constant volume processes, okay, when the volume is no change, has no change, means zero expansion means no work done. So your W12 is 0, so you have only Q12. Simple. Okay. So constant pressure process somehow. So this results changing enthalpy. Okay. We have done this very well. I believe you have the notes. There are records as well. So later I will summarize the videos for these cases and email to you. Okay. So you have to understand this very well. So please note down this. Please note down this. So from polytropic process, one special process is constant volume. Another special process is constant pressure. So means the pressure unchanged is constant pressure, volume unchanged is constant volume. So when there is a pressure and volume change, so the PV to the power n equals constant. I hope you can remember. It's about this polytropic process, and n is the polytropic index. Okay, so you have to know this very well. And this W12 polytropic process, the work done will be given, okay, in the exams. Yes. So constant pressure process, heat addition is this, is H2 minus H1. Constant pressure heat addition is enthalpy difference, okay. Constant volume heat addition is internal energy difference, okay. So you can see these things, okay. So here for constant pressure process, W12 is, of course, pressure times the volume increase. See, so since this is delivering, sign convention is there as minus because we consider V2 is expansion from V1. So V2 minus V1 means it's a big volume. So this system has done a work. So this reduce some energy. So W12 is minus, okay. So you have to understand this, okay, very important. And adiabatic and isothermal process, remember PV to the power n, when n is 1, PV equals constant is isothermal process, okay. But anyway, formula will be given for this case in any case if I'm asked you to work on something. So isothermal process, the beauty is the net work plus net heat becomes 0. Okay, because no change of internal energy, constant temperature, that's why. Q12 plus W12 is U2 minus U1. Since isothermal, constant temperature, U2 is U1, so Q12 plus W12 is 0. Okay, because internal energy, the temperature reflects the internal energy. So these things we discuss. So adiabatic is reversible. Okay, reversible process here, PV to the power gamma equals constant. Okay, isentropic process with no heat transfer. See, Q equals 0. So reversible with no heat transfer. Okay, so this one will be given in the exam. So W12 is, of course, here you can see when Q is 0, W12 is U2 minus U1. So U2 minus U1 is W12 is given here. So these are the things basically you have to look into. Okay. Yes. R is in PV equals MRT. We will look into this gas laws as well. Okay. So make sure you know these things very well. Okay. You know these things very well. And these equations will not be given because this is the energy balance or the first law of thermodynamics. For closed system, these things you should know. Okay. If this is given means you don't know the basics. Yeah, that's all. So go through the notes, go through your the text I passed to you many months ago, and make sure you know this summary. Okay. With that one, look into this kind of questions. Okay. Yeah. So this is an example here. You can see, yes, you can see this kind of application. So determine the work done. Yeah. So this is constant temperature process. Okay. Temperature inside the cylinder remains the same. Then internal energy will rise. Yeah. So you have to look into this. And under non-flow processes, these 10 questions you should answer. Okay, even there can be answers as well there. So you have to answer this and pass to me this. Okay, because I have to make sure that you do this. Okay, this is from the text. Okay, non-flow processes. Then after that, steady flow energy equation, SFEE. These are the formulas. We have derived this very well. Okay. Then simplified forms for boiler and condenser. Okay. Nozzles and diffusers, turbines and compressors. And for throttles like expansion devices, capillary tubes, and even porous plugs. Okay, there can be restrictions. So this kind of cases you have to look into. So turbines and compressors, nozzles and diffusers, boilers and condensers. See, boiler, opposite is condenser. Nozzle expands. Nozzle, the velocity increase. Diffusers, velocity decreases. Okay. Turbines and compressors, like opposites. And the throttles. You have to make sure, and make sure you will do this as well. Okay, this is tutorial 3 of SFEE. So these things, please take note this, okay? Non-flow process, this one. So now I'm going to share with you the notes, okay? Share with you the notes. See, tutorial 3 is here, okay? Tutorial 3. See, many examples. Yes. See, boiler, turbine, condenser, feed pumps. SFEE expressions, okay? Examples. So you should look into this. We have done this, the basics, okay? So you do this. By next week, you should respond to me, okay? That is very important. So look into these things. Okay, steady flow processes. You can see if I, yes, okay. Boilers and condensers, you can understand this. Then even examples, nozzles and diffusers, there are examples with some explanation. And then turbines and compressors, there are examples. Okay, and throttling devices, there are examples. So all this cases, you have flow in and flow out. That's why these are open systems, steady flow systems for these cases. See, in and out. While having flow in and flow out, there are heat and work interactions, Q and W. Okay, so you have to look into this. So this basics, properties of steams, dryness fraction, same way other refrigerants also two-phase. You have to understand this. Okay, so these are very basics. Okay, I hope you can understand these things, Putala. So I think today, I don't know whether I'm a little fast or not. Am I too fast today? Yes. Revision. The basic components, okay, of this steam power plants. So you can see here, yeah. Let me share this. This one, see? Turbine in, out. What is in working fluid, out, expands through the turbine, work is done. Okay? So W out is, it's very simple, H1 minus H2. Then come to the condenser. What? Working fluid. When passing through this, okay? Heat released, see, low temperature is over here. So Q out is H2 minus H3 here, okay? So Q out. Then totally liquid comebacks and pumping to the boiler pressure, feeding the boiler, okay? So we call feed pump. So work done on the system, on the working fluid. Work done from the working fluid, W out. So there is a W net, W out minus W in from the pump. And the Q net in, Q in minus Q out. So the Q net is W net, that's how the energy is balanced. Okay, so this is quite interesting. So four major components, okay. So when it comes to power generation, steam turbine technologies, there may be some little more improvements, but when it comes to the basic cycle, this remains, okay. So this is related to steady flow energy equations, okay. So basics, you know about this. So now we look into further on this. So let me take a refrigeration cycle. Is it further down or further up? We'll see. Yeah, this is power generation cycle. I will put this. Anyway, ranking cycles, we have done this. So before it cycles, I prefer to look into the refrigeration system. Yes. Yeah. This one. Okay. So let me duplicate here. No issues. We have learned about refrigeration very well. Even we have drawn the TS diagrams, pH diagrams, and many. We have learned about this, okay? So here also you can say pumping heat out. So this is something special you have learned. We have spent few sessions for this. So even pH diagrams are there. So understanding this power generation and refrigeration cycles important. Okay, so power generation and refrigeration cycle. Okay, so that is very important. Okay, so let me put some notes here. Okay, so some knowledge. This may be the technology. Yes, technology. Yeah. So expectation from you. Technology. So we may be asking about the practical aspects. Practical aspects. I'm simply putting some. Let's say in steam power generation, after expansion, why the steam becomes, becomes saturated. Why the steam becomes saturated? Okay, why the steam becomes saturated? Or let's say this way, why the steam becomes saturated or wet? Yes. So maybe we can give you a ranking cycle. You can see after expansion, saturated. So why? Why the steam becomes saturated? Any technology explanation? Okay, technology explanations we may be asking. See, example. Here itself you can say, see, saturated or wet. Here, point number 2. So the question has a relevancy in steam power generation. Okay, so we will be asking, because we have explained this very well. Yes, then you should be able to technically address this. Okay, there can be many things, not just this one. Okay, not just this one. There can be many other things. Let's say, so this is in steam power generation. Maybe in refrigeration. Okay, refrigeration. What are the components responsible for the maintaining of high and low pressure sites? Yes. What are the components? And okay, and explain, okay, how that works. So you have to answer. Okay. So there can be many other things as well. So explain the flashing. We have discussed this. And its application of having a liquid cell in refrigeration. Yes, we can ask this kind of things. See, tech knowledge. Yes. Explain how a refrigeration system can be used as a heat pump. Yes. So write down expressions for COP in heat pump and refrigeration, and justify that COP of heat pump is always higher. Yes, you have to answer. Maybe there can be mix of this. Yes. Some more maybe. Yes. In the beginning of the starting of a vapor compression, refrigeration system, let's see, after the starting system, it may take a little while to perform cooling. Explain. Yes, we have discussed these things, so you have to answer this. Okay? You have to answer this. Okay? So what are the key components of vapor compression, refrigeration systems? Because some are good in explains, some are good in maths. So we have to be fair to everyone. Okay. Key components. Yes. And then, yes, explain the 5 steps. 5 steps in refrigeration. And refrigeration, how to say, explain the 5 steps in refrigeration. Let's see, refrigeration solutions. Okay, 5 steps. We have learned about 5 steps. So we can ask a lot of things. Yes, we can ask a lot of things. And why the enthalpy of refrigerant passing through the capillary or expansion device remains the same. Okay, is assumed as remains the same. So we can ask about these things. Okay, so same way power plants. So power plants also we can ask the same. Okay, let's say in power plants. Okay, in, let's say, steam power plants. Steam power plants. Steam power plants. So you can say the cycle has many similarities with the reverse refrigeration cycle. Discuss. Okay, with the reverse, with the reverse refrigeration cycle. Discuss. Okay, so how do you define the efficiency? See? And what are the key to consider for the best possible efficiencies? Yes, we can ask these things. Not to say this, but we can ask. Okay, because these are practical aspects. So whatever we are asking, the questions that we have discussed. I can remember flashing, we have discussed 2 sessions. So we can ask about the steam power plants. Okay, power plants. There could be many things. Yes. About entropy minimization. Okay, minimization. We can ask about this. Okay, so this are technology. Okay, technology. Very nice. Some more. We have to check your understanding of entropy. We will be testing. Yes. Understanding entropy. So here about clauses. Okay, CLAUSIUS. Clauses. Equality. When stands. If not, how would be the expression for clauses? Yeah, with the lucky we came back. Okay, about the clauses inequality. Clauses inequality. Okay, then okay, for gas power cycles, let's say, considering the clauses okay, statement, let's say, statement, sketch the TS diagram for the Otto cycle. Yes, possible. Otto cycle. Yes. So, what says from the Kelvin Planck statement. Okay. Yes. So you can learn a lot about this. Okay. What are the possible considerations of entropy in improving engine efficiencies? Okay, discuss. So we can ask anything because we have explained this. Okay, Udana. So I will send this to you. Today, maybe even you can note down this. So understanding entropy is very important. It's related to tech knowledge. Okay, entropy has a lot of practical aspects. Okay, entropy has a lot of practical aspects. Yes, and we have discussed about a kettle design. You didn't do this, but there will be a little question, okay, a question asking some design considerations. Okay, so this will be there as well. So I will put minimum 8 questions. Okay, a kettle design. Okay, kettle design about the heat transfer. Yeah, very simple. Okay, so these are, anyway I will guide you for the answers for this. Okay, I will guide you for the answers for this. So we can ask many. So tech questions, I will put minimum 3 tech questions, including 1 innovation question. Okay, so then you will be looking into, okay, then you will be looking into power cycles. Power cycles, Carnot cycle. This can be for any gas or vapor, but Carnot cycle, and then the gas and vapor power cycles. Okay, so gas and vapor power cycles. So under this, yes, vapor power. Yes, we will look into the Rankine cycle. So we have developed this. Okay, so gas power. So you have learned about Otto, diesel, dual, and then the turbine engines. This is Brayton. Give me a second. Oh, that is okay. Brayton cycle. So here we are not going for big analysis, but we will ask qualitative questions containing tech, okay, knowledge, okay, and little analysis. In that case, formulas will be provided. Analysis. Formulas will be provided. Okay, this one. So revision 1 today, if you look into this, please do this and pass to me. Understand this, understand this, understand, and do the examples, do these things, pass to me as CS. After that, open systems, steady flow energy, understand and do this CA and pass to me. Okay, so there will be around 3 questions from non-flow and steady flow. There will be around 3 questions. Okay, so you have to expect that. So some tech knowledge about this. So power plant, there will be 1 question. Refrigeration, there will be 1 question. So gas and vapor power cycles, there will be little questions, and then some balance is there with descriptive type. technology explanations and little analysis. Okay, so we will go for a balance. Okay, so when you can give me this tutorial 3 and non-flow process 10 questions and the steam tables, you should do this, because without doing, one way it's a C, it's for CA, and the other way it helps for your exams. Okay, so today is revision 1. So any questions, Budala? Any questions? Any questions? Ruben? Yes, Piris? Any question? So this week, so let me email you this. So focus should be in this, of course, closed systems, non-flow systems, open systems, steady flow systems, and little questions are there. You have to understand this. And then steam table, the reading of this dryness fraction related parameters, calculations, you have to have that knowledge, because without that basic knowledge, very difficult to do a vapor power cycle analysis. So sometimes with the steam, we can have closed or non-flow system questions. Okay, so you have to do that one. Paris, any question, Puta? Any question?
Excuse me, sir, අපට මේ අර සමහර ප්‍රශ්න වලට උත්තර දෙන්න අමාරු වුණොත් සර් මේ කියන්නේ මේ ලියා ගන්න බැරි වුණොත් අපිට ආන්සර්ස් ටිකක් පුළුවන් නම් සර්ට පුළුවන් නම් දාන්න පුළුවන් නම් ඒක ලොකු දෙයක් සර්ට අපිට ආන්සර් කරේ බලලා පොඩ ප්‍රශ්න තීරුම් ගන්නට පුළුවන් නේ සර්.
නෑ අපි මේ ටික ඩිස්කස් කරමු පුතා. Don't worry. Don't worry.
හරි සර්.
ප්‍රශ්නයකට උත්තරේ නෙවෙයි පුතා. මේ ඒ කියන්නේ හරියටම මේ ටෙක්නොලොජි කියන එක අපි තේරුම් ගන්න තමයි බලන්නේ. මම මේ නිකන් on the spot මේ ටික ලිව්වේ. ඔව්. ඒකට මේ වගේ questions ඕන තරම් අපිට දාන්න පුළුවන්. ඕනනම් ඔය කට්ටිය වුණත් ප්‍රශ්න ටිකක් එවන්න, we can consider to put into this. Okay, tech questions, tech knowledge.
Okay sir, thank you. Okay sir, thank you.
Yes, even you can propose questions we will put here, because this is to reflect some reasonable good knowledge. That's it. Yes, Ruben. Yeah, you also can propose. Okay, these questions are good for the paper. Shall we put this? So I can consider putting that. No issues at all. Yeah, when it comes to tech questions. But of course, when it comes to maths, maybe I have the liberty to put into this maths questions. But basic, once you have this basic know-how, and if you do this one, I will assure that answering the question you are facing in the exam for such nature in open and closed systems would be easier. With that. Okay, so paper will be quite standard in the sense thermodynamics is a grand subject, you know, so you have to respect.
The exam when you near future third semester start karwana.
Depends පුතා. මොකද තාම මේ semester 6 එක තිබෙත් නැහැනේ අපි. semester 6 එක තිබෙත් නැහැ. කින්ද බොහෝ වෙලාවට fourth semester එක පටන් ගන්න තියෙන chance එක වැඩි. ඒකයි. third semester එක පටන් ගන්න තියෙන chance එක වැඩි. possibility එක වැඩි. ඒ වුණාට එහෙම කියන්න බෑ. මොකද මේ exam එකට මට හිතෙන්නේ මේ වගේ වෙයි. ඒ කියන්නේ overlap එකක් tie සතියක් දෙකක හරි පුතා. ඒකයි. Don't worry about that. But we will look into this. So පුතා මේ ටික හොඳට දැනගන්න ඕනේ. අර දීලා තියෙන note එකේ තියෙන ටික හරිම ලස්සනට දැනගන්න. ඒ කියන්නේ වීඩියෝස් තියෙන ඒවාට මම ඒ ටික arrange කරන්නම් ගන්නට. ඒ ටික YouTube එකේ තියෙනවනේ. ඒව හොඳට කියවා. ඒව හොඳට බලලා මේ knowledge එක ගන්න ඕන පුතා. තේරුණා නේද? natural understanding එකක් ගන්න ඕන. ඒකයි. මේ natural understanding එකක් ගන්න ඕන. මම හිතන්නේ ඔක්කොම ටික YouTube එකේ තියෙන්නේ. Let me organize this. Okay? මොකද ගොඩාක් තියෙනවනේ මටත් මතක නෑ. කින්ද let me organize these things. And I believe that you have the notes, all the notes as well. Even this note should be with you. About this, let me share that note again. That's about the steam property evaluations. Yeah, that also should be with you somehow. Somehow should be with you. See, this kind of things. So those days, these were well explained. Okay? Okay. Magic balagan somehow it is very important. And even for manufacturing, we are going to do this applied thermodynamics. For mechatronics students, even you can look into the projects. Even final year project or design project, you can work on thermodynamics related technologies to look for solutions. Maybe refrigeration or power generation or even construction of turbines, whatever. Yes, we can look into this. Yeah. So your knowledge is enough, but what we need is mainly the creativity. Creativity, something, if you can imagine well. So the rest we can look into. Don't worry. So vapor power cycle happened to be the last topic in the syllabus. So vapor power cycle analysis. There you can see isentropic compression and isentropic expansion, two processes mainly. And some cases, constant volume heat additions, some constant pressure heat additions in dual cycle both, okay? And the Brayton cycle, it's a bit different. So even when you have the basic understanding of this polytropic processes, and then this adiabatic processes. Yeah, mainly if you know the polytropic process, then you can look into this. Okay, here the reversible adiabatic processes. We can look into those as well. Don't worry. Eh? Yeah. So even though today happened to be the first revision, this is for your upfront preparation for the exam. So other than that, we will take one more session maybe to look into possible, not to say additions, but little more extensions of this existing subject of interest. We can look into that because we have time. So March is coming. So we have 2 weeks. So next week we will wind up the revisions. Okay. So next week will be our revision 2 session. Okay. Revision 2 will be next week. Don't worry. So you will be better off, but make sure this tutorials, you should do that, because here in the discussion, this first 2 means you have 3 questions there. Okay. You have 3 questions. Don't worry. So today, I think that's all, Vitala. So understanding entropy, very important. Okay. So look into this, and the power cycles. You should look into that as well. And of course, we have done some modeling of, okay, heat engines. We have done some modeling. Can you remember the modeling we have done? High temperature reservoirs, low temperature reservoirs, the work done, network done, and we talk about the efficiencies and all that is for the power cycles. Last week we have done that. Thermodynamics. (19.2). If you look into this, thermodynamics 19.2. Where is this? We have learned about this modeling. This modeling part we have done. So, very important piece of knowledge. You can see here. See modeling part. High temperature reservoirs, low temperature reservoirs, the work done, the standard cycle. Okay. Then gas power cycle systems, vapor power cycle systems, some comparisons. We have done these things as well. So we have a lot of things we have done really. We cannot put all into the question paper, but we will have a balance of the technology, the true technology, your little basic analysis, the closed systems and open systems and energy balances, and some classic knowledges like entropy. So we will talk about this, and very important to know about reading the property tables and all. So working fluids. So these keywords for sure will be in the exam paper. So I think that's all for today. Okay, that's all for today, revision 1. So if I add that, also here, where is that? Copy. Yes. So these things will be there. Okay, the modeling part. So I will discuss this again in the coming revision 2. Then you will have more idea about this. So go through the gas power cycles and the vapor power cycles, the basics, and we will have little analysis as well. So that one next session we will do it. So enough for today. Get ready for this. So let me save this and email to you. Yes, I've sent you today notes as well. So that's all, Putala. So before winding up, any questions? Don't worry, even I will put this video also in the web so that you can go through this together with the notes. But your note is quite okay here. So look into this. Hasita ternada puta kiputika? Okay, need?
Oh, sir.
Oh.
Oh, sir.
Today no much thoughtful things like previous sessions. Okay, no much thoughtful. So just something about exam focus. So this is nothing much to be that philosophical, no much things, but anyway, you go through this, Mutala, you go through this. So you not, so I will not give any question outside your note. Okay, but of course, when it comes to some tech knowledge and all, so I will look into our supplementaries like what we have developed the notes. Okay, so out of 8, maybe 4 questions, that what I'm expecting, or maximum maybe 5 questions for you to do. Yeah, out of 8. Okay, Bhutade, that's all. So today nothing much, and seems very simple because it's only some reminding only. So see you next week then, and please do the assignments and pass it to me. That is for you really, yeah? So there will be 3 questions out, minimum 3 out of today revision. There will be minimum 3, actually around 4 questions out of today revision. So next week we will have another 4. Okay, Bhutala? Good. Yeah. So 2 more weeks we can do revision, then we will be all right. So anyway, you will receive a lot of work, but no choice, Bhutala. So good subject, this one. So you have to answer really, then you will get full marks. Yeah. So anyway, I will try to put some balanced way. So those who good at maths, they can do some analysis, and those who good at technology explanations, they also have some. Even those who can think and write something, creativity and innovation, they also have some questions. Yes. So we will do it that way. Okay, good. So thank you, Bhutala. So let me stop the class. Bye. Bye.
Thank you, sir.
Okay.
Thank you, sir.
Thank you, sir.
Thank you, sir.